Hello friends, today we'll learn the topic Hysteresis loop of magnetic material under the course Fundamental of Electrical Engineering. Myself is Mr. J.M.Patil, Senior Lecturer, Electrical Engineering Department, KK Polytechnic, Nasik. Now before we discuss the hysteresis loop in detail, we'll first define magnetic hysteresis term. So magnetic hysteresis will be defined as when a magnetic material is subjected to cycle of magnetization and demagnetization, it is found that the flux density in the material lag behind the applied magnetizing force H. This phenomena is called as magnetic hysteresis. In short, we can define the magnetic hysteresis as the phenomena in which the magnetic flux density in a material lag behind the applied magnetization force. Now to study the hysteresis loop and how to plot the hysteresis loop, we have to do an experiment, and for it we require the circuit arrangement. The circuit arrangement for plotting the hysteresis loop will have certain arrangement, and the first important is that we must have the electromagnetic part, and that part will be nothing but a coil which will be wound on a iron ring. The second arrangement that will require to reverse the direction of current, and for it we required a reversible switch. And third is that we require to change the value of the current that flows through the coil wounded on an iron ring, and that is possible by varying the resistance or rheostat. Whatever these three basic arrangement requirement is shown in the next diagram, or what we call it as the circuit diagram to plot the hysteresis loop. On the right side we observe that there is a iron ring of circular cross section, and it is being wound with a coil of few number of turns. Let us see that n is the number of turns of this coil. This coil will have two ends, one can be called as start, another can be called as end, and these 2 points or start and end terminals are connected to a switch which is a reversible switch. We require to change the direction of current that can flow through the coil wounded iron ring. For the direction of current shown, we can call it forward direction. If we change this switch position, then this direction of current will be reversed. That means that current will flow from the right side to the left side in the circuit diagram. This reversible switch is connected to the DC source, that is a battery, through an ammeter to know what is the amount of current that flows through the coil wounded iron ring. And to vary this current we require a rheostat. The rheostat will have the two position, one is the minimum position, another is the maximum position. When rheostat is at maximum position, whole of the resistance is being circuit in the circuit and the current will be minimum. When we move that rheostat from right to left side, whole of this resistance will be cut off and we get the minimum position. That means the current will be maximum in the circuit of the coil wounded on the iron ring. Whatever this arrangement, one thing we have to here understood that the magnetic ring should be subjected to a cycle of magnetization and demagnetization for both direction of the currents, that is the forward and reverse direction. If we do the forwarding and reversing direction of the current, and we measure the value of current and corresponding magnetic flux or flux density, then we will get a graph which is known as the hysteresis loop. It is the graph between the magnetic flux density and the magnetic field strength H. If we want to get more detailing of this hysteresis loop or how we have plotted this graph, then this graph will start from this origin, and when we go on increasing the current in forward direction, then first we reach to the A point. If we further go on increasing the current, it will be a straight line where magnetic flux density will be directly proportional to the magnetic field strength, and after some value of magnetic field strength there will not be any increase in magnetic flux density, which is called as saturation point. After this point, if we again reduce the current in the same direction that flows through the coil as is shown in the previous figure, then that value of decrease of current will also decrease the magnetic flux density or magnetic flux in the coil, but it will lag behind the decrease in magnetic field strength H, and we will end up at the point B. The point B where the magnetic field strength H has become 0, but it have certain value, and that we called as the magnetic residual magnetism. So OB is the residual flux density. Even when the H has become 0, there is some value of the magnetic flux retained by the magnetic material, and this property is called as retentivity of the magnetic material. Now after this point B, if you further decrease the current but in the reverse direction, then we'll get the point D on the graph, then point E. Look at the point E. The point E on the graph is the point when we see that the magnetic flux density has 0 and there is certain amount of magnetic field strength or magnetization force. So this OE gives the coercive force necessary to make the magnetic flux density to the 0, and it will be in reverse direction, that is in the negative value of this force S is needed to reduce the flux density to 0 value. Further point, if you go on the decreasing current, now here decreasing means increasing the current in the negative direction, then we'll get the point finally F point. F point is again the saturation point, but it is in the reverse direction of the current and magnetic flux. From this point again go on decreasing current to its 0 value, we will get this graph and we will again come to a point, that is G. Now look at the point B and G. These are at the same coordinate from the origin. So OG will also be the residual magnetism, and it is the residual flux density BRS here shown. This is the flux density when H has become 0. If further we go on increasing the current now in again forward direction here, then we will see that the magnetic flux density has increased, then it will 0 attain value at the H point, which will be again the coercive force in positive direction needed to reduce the negative value of magnetic flux density to 0. Further increase in the value of current, that is H, will again reach to the point C. So this C, then D, E, F, G, H, and again C. Whatever these external lines and direction here you can observe is being termed as the hysteresis loop. Hysteresis loop will require the magnetization and demagnetization of the magnetic material in the both direction of current, that is the forward direction of current and reverse direction of current. From this graph we can define now the different terms that are usually related to hysteresis loop. First term is the residual flux or residual flux density, the value of flux that remain in the magnetic material even when the magnetic field strength has become 0 will be called as residual flux. The residual magnetism, the corresponding flux density at the residual flux will be called as residual magnetism. The retentivity, the property of the magnetic material to retain magnetic flux in it when magnetic field strength has become 0. This is the important property when designing the material for the making the permanent magnet. Then coercive force, to wipe out the residual flux in the core, the required magnetizing force in opposite direction will be called as coercive force, we have just seen in the previous graph. And magnetic saturation, the flux density remains constant in spite of change in magnetizing force is called as the magnetic saturation. These 5 terms are related to the hysteresis loops that we have seen in the previous slide. Now let us know the hysteresis loop for two basic category of material. The figure A shows the hysteresis loop for the hard magnetic material and figure B shows for the soft magnetic material. If you carefully observe these two loops, then the hysteresis loop area will be more for figure A, that is hard magnetic material, and it is less for the figure B, that is soft magnetic material. Here in the figure A, that is for hard magnetic material, there will be high value of residual magnetic flux or flux density and high retentivity is there. High value of coercive force is observed here. It means that this kind of material can retain the large value of magnetic flux within it. So this material will be suitable to make the permanent magnet, because that are to be used for the longer period of time. If you observe the figure B, which is of soft magnetic material, we can observe that the area is less, there is less value of residual magnetic flux, there is less value of coercive force, but as the area of this loop is less, there will be less amount of the loss in this particular material, because when we have to forward and reverse direction of current through magnetized and demagnetized material, we require certain amount of energy, and that appear as the heat in the magnetic material, which is known as hysteresis loss. So this magnetic material soft will have less hysteresis loss, so they will be suitable to make the magnetic core of the various electrical machines. And here we have large value of the permeability, the slope of this graph. If you draw from its center and extreme point, then it will have the more value of slope, thereby we can get higher value of relative permeability, which is desirable in making the core of electrical machines. After studying this topic, what are the questions that are being asked on this topic in the previous examination? Here are listed. Draw the circuit diagram to plot hysteresis loops. So hysteresis loop, if you want to plot this loop, then we have to draw the circuit diagram. We are described in the slide number 3 here. Then second is the describe the steps involved in plotting of hysteresis loop. Here you have to describe the process that the current increases in forward direction. Then second step is that current decreases in forward direction. Third, current is increase in reverse direction. Fourth, current is decrease in reverse direction. Then increase the current in forward direction. By this you can describe with the help of that hysteresis loop the steps involved in plotting hysteresis loop. Define the hysteresis and hysteresis loss. Hysteresis we already defined. Hysteresis loss is the amount of the energy required to move the magnetic material through magnetization, demagnetization, and that energy appear as the heat in magnetic material. This is known as the hysteresis loss. Draw the hysteresis loop for ferromagnetic material and label its parts. So whatever the graph we have studied, that graph itself is of hysteresis loop for ferromagnetic material. You have to mark the point of residual magnetism in positive negative direction, coercive force in positive and negative direction, and saturation points. Define the term residual flux, retentivity, coercive force, and magnetic saturation that we have studied in the previous slide. Draw hysteresis loop for hard steel and soft iron. That is, I have already described is that the loop with larger area will be of hard steel, the loop with the less hysteresis loop area will be of soft iron. By referring to our video, you can answer these questions very in the model answer type category. With this, we will conclude here. Thank you to all of you.